Okay, so now we are on work view field 5, and we wanted to have 40 micrometer in view field. So this is like almost 10 times. So now we have a very good focus. So we change back to 40 there now. And then it's nice to write it into an even number like 40. And why do I talk about view field all the time? The view field is the width of the image in physical units, in micrometers in this case. So the side of the image will be 40 micrometer wide. And the reason why I talk about view field instead of magnification is that magnification is actually a very weird thing to talk about in this, what shall I say, scientific concept. Because magnification by definition is the size of the image versus the physical size of the object. So that means if I take an image and then I print it in a journal, the physical size of the image in the journal is not the same as the physical size of the image on my screen. So the magnification by definition is actually different. So magnification is a very bad way of describing how zoomed in something is. View field is a much better, because 40 micrometer view field is 40 micrometer view field no matter where you print it. All right, so we can remove the small window. So now if we want to scan this image now, we can configure different scanning parameters. So if you go to the menu on top there called SEM, you have something called image parameters. Click on that. And this window has, you go from top to bottom. First it says the live and says 1 by 1. You can change the aspect rate of the image. Sometimes you have a very thin and narrow sample, then 2:1 can be efficient, but today we want to do 1:1. That means a square. Then we have the size in pixels of the live window, 512. We want that to be small because that gives us a higher frame rate. If we choose a, what shall I say, large pixel size, everything becomes sluggish, and we always try to avoid that. But in the save image, we want to have a higher resolution. So here it says 1500 now. We can try 2000 there, for example. And then we come to the averaging section. And as I said earlier, gray means disabled and blue means it's on. So now it's enabled, it's gray, that means it's off. So we don't do any averaging. And then if you click on the one that says save, it says frame accumulation, line accumulation, and drift corrected frame accumulation. So what's the point of averaging? So step 1 to understand is everything in scanning electron microscopy and many other kind of signal acquisitions techniques is that we're talking about signal to noise ratio. We want to have a strong signal and little noise. And there is like good ways of accomplishing this and less good ways of accomplishing this. And the best way of doing it is to make sure that the signal is strong originally. Mm. In electron microscopy, that means high beam current. If you have high beam current, the signal to the detector, emitted electrons, will also be strong. And then you get a strong signal. You should always aim for that first, because strong current means good signal in the beginning, and you have to do less down the line. If you can't have high beam current, and that can be because of resolution, you want to have high resolution work, it can be of a beam sensitive sample, it burns up, then you need to fall back to other methods. And the second best thing is to increase the scan speed. So you scan for longer time. That also improves signal to noise ratio. But you pay by time. So if you can have high beam intensity, as I said initially of this lecture, we can do an image in 30 seconds or 10 seconds. And we can have a much efficient workflow and manage many, many samples on a full workday. But if we need to scan long time because we are forced to work at low beam current, then we can suffer scan times that is 1 hour per image, and suddenly, instead of taking one image every 10 seconds, you get one image every hour. So it's like 8 images for that working day. So that is the second thing you want to do. But then it can be that if you have a bad sample that is charging, scanning for a long time makes it drift away, and it makes it impossible for you to scan for a long time. Then you need to fall back on the third last line of defense, and that is integration, or averaging as it is called. That means we can do frame accumulation. We take several frames and then digitally we sum them up. That improves signal to noise ratio. So if we scan, 10 images, 1 second each, the total scan time is 10 seconds. So we will have the same signal to noise ratio as if we instead would have scanned one image for 10 seconds.
Yeah.
But since it's scanning so fast, drift will be, of a less concern. So that is the only reason. So we don't want to do averaging if we can avoid it. And then line accumulation is that we, instead of scanning the whole image, we scan one line 10 times, and then the second line 10 times, and third line 10 times. There are different, scenarios when one is better than the other. And I think that's outside the topic of today's lecture. Drift-corrected frame accumulation is, a more modern approach. And that is when you scan one frame, due to the charging, the next frame will be offset. So if you scan that, if you just sum them up, it still will be some smearing. So drift correction is that you digitally rematch each single frame so they line up, and then you add the data. So it's a software-based correction for that drift. But as I said in the sputtering session, when you're starting to need drift-corrected accumulations and so on, you should stop for a minute and think that why not improve the coating of the sample? Yeah. Because when you end up in this scenario, you will spend long time trying to get a good image, lot of, configuring and fiddling to compensate for this drift and so on and so forth. And when you can just unload sample, go and redo the coating, 10 minutes, you're back online, and you will have an easy session. Yeah. So we will not do averaging because sample is quite good, I would say. Then we can see it says acquisition time now, it's 2 minutes and 52 seconds when we do set scan speed 6. So if you click on set scan speed, you see we can choose different scan speeds there, and we see the time it takes. And the top one that says keep actual speed, we don't want to use that because that is the speed of the live image. Nothing wrong in using the same speed, but the problem is you keep changing the live speed when you're running the machine. So in the end, you will end up with that you have taken several images that has been scanned at different scan speeds. And that looks very unprofessional in your publication later on when you see there's one image is very noisy and another image is crystal clear and so on. It's unprofessional to work like that. So we choose a fixed scan speed and run all images like that. And that is also the reason why we choose a fixed view field of 40.0 micrometer. We don't want to have 39.7 micrometer, and then the next image we take is 37.2 micrometer, because then we have small scale shifts between all images. Just looks unprofessional. A fixed view field for all images. So take something that takes this, was it scan speed 5, or you can do that, scan speed 5, and then you click apply. The last part of this configuration is what in the legend bar we want to visualize. Do we want the working distance, the beam energy, and so on? What kind of info do we want? This info that is already pre-selected is nice to have. Yeah, so you can just remove that. And then you can click on the scan image icon, just the lowest, last one. And then it starts to acquire the image. And one can use the scroll wheel here also. So zoom out. I mean, it starts in original. You see, this image doesn't fit on the screen really. It's 2,000 pixels by 2,000 pixels per channel, right? So since we are using 4 channels, it will be twice the size. It will be 4,000 by 4,000 pixels in size. And this takes, as we saw earlier, roughly close to 2 minutes. But we get 4 signals. So scanning them one by one would take 8 minutes. So we save time by doing this.
Yeah.
And the nice thing by in this lecture showing all 4 detectors is that it gives us some time to talk about, what shall I say, the different characteristics of these detectors. So, okay, we come to the save window dialog here. The first here, you can just write some notes. That's a less concern. It's not the file name really. But one can take notes of, what shall I say, the data that we can see here. And especially the thing called pixel size here. This is the physical size of the pixel. It says 19.531 nanometer. So we cannot, at this pixel size, the resolution of the image we're scanning, and this magnification on the machine, 1 pixel is 19 millimeters squared. So that means if we want to see smaller particles, we can do in 2 ways. Either we scan at a higher resolution. Instead of 2,000 pixels, we scan by 4,000 pixels. Then we get 10 nanometers resolution. Or we need to zoom in, basically, change the view field. You got some name there?
Yeah.
It's a very good, what shall I say, policy you're using here also, that in your file name to write what kind of detector you used, what kind of working distance you had, what kind of voltage you have, all these parameters that it's nice to write that in your file name, because then when you have many images, you can easily sort them afterward without opening every single image. But since the pixel size in our scan image is 90 nanometer, we can go and look here now on the spot size on the machine. In our current configuration, we have 15 nanometer in spot size. So it's very good to compare, or important to compare these 2 numbers, because 50 nanometer is less than 19 nanometer. That means the information that is produced by the electron beam comes from a 15 nanometer diameter zone. And the pixel size is 19 nanometers. So all that information fits within 1 pixel. If I would have scanned with 4,000 pixels instead of 2,000 pixels, then each pixel, instead of being 19 or 20 nanometer, would have been 10. That means the spot size would be 50% larger than the pixel size. So that means if we scan by 4,000 in this particular scenario we're having here, the image is just, what shall I say, blown up. The resolution is not improved. It just, if we zoom into one-to-one zoom, the pixels will start to look blurred because the spot size is larger than the actual pixel size.
Yeah.
So in that case, we have to, what shall I say, change beam intensity, for example, in this case, or change scan mode to get a smaller spot size of the beam. And without changing anything, if you click on spot size there, you can choose that hack also. Then you see you can actually change the size of the spot size. Mm-hmm. So if you write 0 there, write 0 and click enter. Then you can see what you're doing then is you're asking the machine, give me the smallest spot size. The beam current that corresponds to the smallest spot size. And then we see that the beam intensity index is set to 10.23. And initially I said that the smaller beam index you have, the higher resolution you have, but it was not always true. Mm-hmm. So here we see a perfect example that beam intensity that creates the smallest spot size is actually 10 in this particular configuration, not 1. Yeah. That is actually good. I mean, we have a higher beam intensity. If you change this to 1, we see the spot size became 8.5. That's almost twice half the size
Yeah.
of what we had 15 before. Change beam intensity to 1 now, and then we can compare what that says. You see, it's back to 15 now.
Mm-hmm.
So it's not always the case that lowest beam intensity gives you the highest resolution.
Yeah.
So you can go back to 16, which was the thing that we wanted to.